We'll start with a brief review of polynomials. If you can write f as the product of these n linear terms, that is, if it has n roots, then it's easy to see that the highest power of x, that is, the degree of f, is going to be equal to n because we're multiplying these n x's together. What is less obvious is that this implication can be reversed. That is, if the degree of f is equal to n, then we can write f as the product of these n linear factors. This is called the Fundamental Theorem of Algebra. The proof is beyond the scope of the solution and too advanced for most high school students. This results in n roots that are not necessarily distinct. And we can further conclude that all non-constant polynomials, that is, those that have a degree of at least 1, will have at least one root. So let's take a look at the problem. We have that the degree of a polynomial p is 2, and it has a constant of 1. The degree of q is 3, its constant is 2, and the degree of r is 6, and its constant is 3. When we multiply the polynomials p and q together, then we multiply the terms with the highest power of x, which are 3 and 2, and so that gives us a polynomial with degree 5. In the problem, we're given that the polynomial p of z times q of z is equal to r of z. And note that this is only true for some values of z, not all z, obviously because the degree of r is 6. And in fact, we are trying to figure out how many values of z and minimize that. So let's take both of these terms and put them on one side of the equation and set it equal to 0. And we'll say that this now new polynomial, we'll call it t of z. Since r has a degree of 6, but p times q has a degree of 5, we won't be able to take away this 6th power of z from this polynomial, which means t of z is also going to have a degree of 6. On the AMC, when we're asked to minimize a quantity, such as n, the number of possible solutions in this case, a good strategy is to eliminate the answer choices, starting with the smallest one. The smallest answer choice given is a, which is 0. But we saw earlier, by the Fundamental Theorem of Algebra, that all non-constant polynomials will have at least one root. Since the degree of t is 6, we know that 0 roots can't be possible. So we eliminate option A, and we go to option B, which is 1 root. Again, since the degree of t is 6, let's try, for example, something like this, z minus 1 to the 6th power. This polynomial has one distinct root, z equals 1. We have a lot of choices for p and q, so let's pick the simplest examples. The degree of p is 2, so it's going to have a z squared term, and its constant term is 1, so let's just write it like this. Q of z has a degree of 3, and its constant term is 2. Since we have this relation, let's solve for r of z. And we'll substitute. We need the constant term of r to be 3. And we see that the constant term for this first polynomial raised to the 6th power is 1. This constant term is 1, and the constant here is 2. Multiplied together, we get 2. And we do, in fact, get a constant term of 3. If we had chosen different polynomials for t, p, and q, to get the constant term that we want, we could adjust t by multiplying it by some constant. So we see that we can get one solution that's distinct, and we can stop evaluating the other answer choices, and B is our answer.